Hello everyone, welcome back to MrMiers Math Channel. Today in Chapter 10, Day 6, we're going to talk about combinations. So we're going to talk about how to perform a combination and how to do it in our calculator, and then we're going to elaborate on what a combination is and how it's different than a permutation. All right, so let's get into it. So first, a combination is a selection of R objects from a group of N objects where the order is not important, and that's key. Order is not important. All right, so the number of combinations of n distinct objects taken r at a time is indicated by NCR, just like for permutations, it was NPR. And it's given by the following formula. So notice we have permutations involved in the formula, and then we also have factorials involved in the formula. Now, NPR is just n factorial over n minus r factorial, and then how combinations is different than permutations in terms of the computation is we have to also divide by this r factorial. Now let's try this one first. So 6C2. All right, remember if we're using a TI 83 or 84, we can hit math, go to probability, and then click that NCR option and we could type it in from there. If we're choosing the TI 30XS, we hit probability, choose NCR, and just press enter. All right, if we do this, we'll get 15. So 15 combinations if we are choosing, if we have 6 objects and we're actually choosing 2. So now let's elaborate. What's the difference between a combination and a permutation? Well, for permutations, order is important. For combinations, order is not important. That's the basic difference between permutations and combination. And what we really mean is that for permutation, a different ordering of the objects would be 2 different events. And then for combinations, a different ordering of the objects would not be 2 different events. Okay, so a lot of times I like to use the analogy, permutations are like races, whereas combinations are like teams. Okay, so let's continue to elaborate here. If we're looking for the possible permutations of the letters A, B, C, and D, and we're choosing 3, the permutations ABD and BAD are different events because the order of the elements is different. Okay, A is first in this first arrangement, and B is first in that arrangement. So that's 2 different events. However, if we're talking about combinations, ABD and BAD would be the same event and not counted separately. Okay, the same elements are in that same group of 3. For combinations, it's the team that matters. So just the people that are on the team, and we can see that in ABD and BAD, we have the same people that are on that team, or the same elements in that group. All right, so let's go on to some examples. All right, let's say Jamal, Kay, Lee, and Max have volunteered to help a nonprofit organization build houses. 3 of the 4 will be assigned to work as painters, and we want to figure out how many choices are there for 3 painters. Okay, in this case, we got to decide whether the order matters or whether the order doesn't matter. And in terms of deciding that, we just have to figure out, does it matter the order in which these people are chosen to be painters, or does it just matter that those people are chosen to be painters? And in this case, I would think that the order would not matter. Okay, once those 3 are chosen, they're all just going to paint. Okay, so this is a combination. And of 4 objects, we're choosing 3. So that would be 4C3. If we type that in, we get 4. Okay, now just to distinguish the difference between computing a combination and computing a permutation, all right, the permutation of 4P3 would be 4 factorial over 4 minus 3 factorial. And once we do some simplifying, it's just we have 4 people to choose for the first painter, 3 people to choose for the second painter, 2 people to choose for the third painter. Okay, this is different from combinations because for combinations, 4C3 is going to be 4 factorial on 4 minus 3 factorial times 3 factorial. So n factorial over n minus r factorial times r factorial. So obviously we can see mathematically why this is different, but why do we divide that 3 factorial? Right, if I write out 4 factorial, that's 4 times 3 times 2 times 1. And then we have 1 factorial times 3 factorial. What we're doing is taking away the number of arrangements of those objects. Okay, so it doesn't matter the ways that we can arrange those 3 objects. It just matters that those objects are in the group together. So we're taking away the amount of ways we could arrange those 3 objects. And that's why a combination is different than a permutation. All right, let's move on here. For summer reading, you're asked to read 2 books from a list of 6. How many different pairs of books can you choose to read? So first we got to evaluate, is this a combination or a permutation? All right, and it says pairs of books. So we have to look at the words carefully. Okay, how many different pairs of books can you choose to read? It doesn't say in what order do you choose to read them. So I'm going to argue that in this case, order doesn't matter. It's just asking about which books did you read. So this is a combination. So that would be 6C2, and we would get 15. In the next part, we have 12 students enter a talent show. Awards are given for first place through 5th place. And how many ways can the students finish 1st through 5th? Supposing that these awards are different, like they say 1st place, 2nd place, 3rd place, and so on, this would be a permutation. Order would matter. 1st place would be different than 3rd place. Of course, if all the awards were the same, then that wouldn't really be true. So this is a permutation, and that would be 12p5. So we would get 95,040 different ways those students could finish 1st through 5th. All right, on to the next one. In example 3, it says, in how many ways can you play 3 of 11 songs on a CD? And it says, let's suppose that the order is important. So if the order is important, that's 11p3, because this thing is a permutation. And if we type in 11p3, we would get 990 different ways. And then in how many ways can a soccer team choose 2 captains from 12 players? This one's very much up to interpretation. The team is choosing 2 captains. So I suppose that these 2 captains are going to be co-captains. You know, not like one is first captain and the other is second captain. These folks are going to be co-captains. So if they're co-captains, then it's a combination because order doesn't matter. And of the 12 players, we're choosing 2. And that would give us 66 different ways we could choose those 2 captains. Now let's go in and talk about multiple events. What if multiple events are occurring? All right, so let's say you need to make a group of three students with exactly 2 girls and 1 boy. All right, there are 3 girls to choose from and 2 boys to choose from. This would be a multiple event. So what we would do is break this down into 2 independent events. All right, choosing the girls and then choosing the boys. So in the first event, we want to choose 2 of 3 girls, so that would be 3C2, and we would have 3 choices for that. And in the second event, that's choosing the boys, we have 1 of 2 boys to choose from, so that's 2C1, and we would have 2 choices for that. So using the fundamental counting principle, it's the number of different ways the first event can happen times the number of different ways the second event can happen. And that would lead us to 6 different ways we could form this co-ed team. All right. Now we're going to use a standard deck of playing cards to talk about probability in future sections, because using playing cards is an awesome example of different ways we can do probability. So we've got to know our standard deck of playing cards. So first, there's 52 cards in a standard deck of playing cards. We're excluding jokers. Okay, 26 of which are black and 26 of which are red. So half of the deck is black, half of the deck is red. In that deck of cards, there's 4 different suits. We have spades, clubs, hearts, and diamonds. There's 13 cards in each suit, so every suit has the same amount of cards. And the cards are as follows. We have 2 through 10. We have Jack, Queen, King, and we also have Ace. Depending on the game, Ace might be, the lowest card or the lowest ranking card. Ace might be the highest ranking card, or maybe it plays a versatile role. Okay, the Jack, Queen, King in each one of these suits is called face cards. So we have 3 face cards in each suit. So it's a lot of information. If you're not a card player, then you may not know this, so you might have to study up these notes on playing cards. All right, so let's get into the final two examples in this lesson. So in example 4, let's consider a standard deck of 52 playing cards. The order in which the cards are dealt for a hand does not matter. Okay, we want to figure out how many different 5-card hands are possible. So if order doesn't matter, we're talking about a combination. And we have 52 cards to choose from, but we're only choosing 5. So that would be 52C5. And for that, we're going to get a pretty big number. So in this case, we have 2,598,960 possible 5-card hands from a standard deck of playing cards. Okay, this is the amount of outcomes that are possible in a game of poker or in a hand of poker. All right, in a hand of poker, we have 5 cards, and when we're dealt those 5 cards, when we look at our hand, the order in which the cards lay in our hand does not matter. We could rearrange them; it would still be the same hand. It would still have the same rank. All right, if we take a look at B, how many different 5-card hands have all 5 cards of a single suit? We could break this scenario down in a couple different ways. One way to think about it is we've got to first choose the suit. So we have 4 different suits. So that would be 4C1. Okay, and then after that, once we choose a suit, there's 13 cards in that suit, and we're choosing 5. So that's 4C1 times 13C5, which would be 5,148. And this is the amount of flushes that are possible in poker. Okay, all 5 cards of a single suit would be a flush, and we have, of course, straight flushes, we have normal flushes, we have royal flushes, so that would be just all the flushes that are possible in poker. Okay, the reason that we had to choose the suit first is because there are 13C5 different flushes in each suit, and then we have 4 different suits that are possible, and that's 4C1. All right, let's take a look at the last 2 parts. All right, next in part C, it says how many different 5-card hands have all 5 cards of a single color. All right, so now we're choosing a color. Okay, so there's 2 colors to choose from. We're choosing one, and then once we choose that color, there's 26 remaining cards. Half of the deck is black, half the deck is red. So once we choose that color, now we're figuring out how many hands we could make in which all five cards are of that same color. So that would be 26C5. So 2C1 times 26C5, and we'd get 131,560 different hands. All right, moving on to part D, it says how many 5-card hands contain 4 of a kind and a queen. Okay, 4 of a kind is 4 of the same cards. So maybe like 4 aces and a queen would be an example of a hand that contains 4 of a kind and a queen. One thing to note is that they can't all be queens. There's only 4 queens in a standard deck of cards. All right, so one option that we don't have to consider is one in which we have 4 queens and then another queen. Okay, so it's going to be 4 of the same cards and a queen. So they could be aces, kings, jacks, 10s, 9s, all the way down to a 2. So we have 4 different types of queens. We have a queen of clubs, queen of hearts, queen of diamonds, queen of spades. And then from there, we have 12 other cards that we could choose from. Or sorry, 12 different options of what to choose from here. There's 13 total cards in a suit, but we can't choose a queen, so that gives us our 12. So 4 times 12 would be 48 different 5-card hands that contain 4 of a kind and a queen. Awesome, folks. So that's it. If you found this helpful or enjoyed it, please like, subscribe, and share. Thank you, and have a great day.